Hello, I'm Radhika Bakshi, and this is my presentation on the paper cuprous oxide photocathodes with band tail states assisted whole transport for standalone solar water splitting. So, the first introduction is that photoelectrochemical PEC water splitting is basically a pathway to store solar energy as hydrogen fuel, and essentially, you need basically a potential to drive the hydrogen evolution reaction and oxygen evolution half reactions, which is usually at equilibrium at 1.23 volt. Cuprous oxide is a very promising p-type oxide photocathode. Cuprous oxide has a band gap of 2 eV, 2.0 electron volt, and nice. It's a nice material to use because of its abundance in earth and its performance potential. The challenge that is associated with using cuprous oxide is that state of the art cuprous oxide uses gold as a back contact. And there are two issues here. That firstly, the gold semiconductor interface is gold is a non-selective contact, which means that it takes up electrons and holes equally. And the problem with non-selective contacts is that recombination can occur if they're not passivated properly, and that is one of the main challenges that occurs with this cuprous oxide gold interface. And secondly, that to get the voltage required, this this material is used as a part of a tandem set, and because it is in a tandem configuration, it needs to be transparent, and the opacity of gold is reducing the light transmission to through the cell. So the aim of this paper is to replace gold with a more selective, a more transparent whole transport layer or HTL to improve the performance and enable efficient tandem devices. So the first, let's look at the experimental methods of the paper. So what they're trying to do is deposit a cost-effective photocathode stack. So what essentially they're doing is taking the copper thiocyanide substrate. Copper thiocyanide is the material that is taken in place of gold as the whole transport layer. And then on top of that, by electrodeposition, we are depositing the cuprous oxide layer, and then either the gallium oxide or titanium oxide by thermal ALD, and on top of that, the hydrogen evolution catalyst. And then the next part of the methodology is to carry out characterization, which is basic structural morphological characterization like XRD, SEM, and then composition characterization like XPS, Mott Schottky, or SL, SCLC, which is the space charge limited current, or whole only devices like optical like UV vis, and so on. So by doing these characterizations and this deposition, you get the results, which are that essentially by going through the structural morphological characterization, we see that the E type, which is Cu, Sc, and E, has more crystallinity and has the 001 orientational nanorods. And CUSA and D has lower crystallinity and multiple orientation and rugged grains. Both have comparable growth rates. And doing XPS, we see that there are obviously the presence of copper, sulfur, carbon, nitrogen, but there could be additional features potentially related to uh, CO2 plus defects and impurities, which we'll talk about a bit later. So the electronic properties is where it gets interesting. So Mott Schottky shows that the p-type carrier concentration in D is much greater than that in E, which is 1.6 into 10 raised to 80 as compared to 8.6 into 10 raised to 60. And the SCLC shows that the uh, conductivity of holes in E is greater than that of D. But the total conductivity of carriers is SCLC shows that the mobility of carriers in E is greater than that of the mobility in D. But the conductivity, once you factor all of these in, turns out that the conductivity for the thiocyanide D is about 8 times higher due to the higher carrier concentration. Optically, we see that the band gap sits similar for both from around 3.84 to 3.95 electron volt, and both are highly transparent, which makes them very suitable for tandem applications. So then we go on to seeing the performance, right? So here we look at more at D type because it is the one with the high conductivity. And it shows that it has a much higher fill factor as compared to the gold counterpart. And it shows that yes, there is a reduced recombination and improved charge extraction. And then there is a higher photocurrent density at operating potentials, which is 5.3 milliamp versus the 3 milliamp. Uh, Quantum efficiency also is really high, about 60%, and the integrated current density is about 5.4 milliamps. So stability-wise, cuprous oxide and the thiocyanide cathode retained about 90% of initial photocathodes over a very long 60 hours of continuous operation, which is very high with very high firing efficiency for H2 evolution. So looking more into the results, we then look into the XPS data, which is the composition data, and then probe at the cuprous oxide and cuprous thiocyanide layer to see what the valence band maxima look like. And then we see that the cuprous oxide maxima is about 0.35, where that of the thiocyanide is about 0.37 or maybe 0.49. Either ways, this shows that there is a small energy barrier for the transfer of holes from the oxide to the thiocyanide. So here, the band tail states really come into play, and for both of them. So these are then arising from these band tail gap defects arise from states that are due to defects like, as we spoke in the past, which was CO2 plus defects. So the mechanism that is proposed by the paper is that from CO2 plus, these the holes then go into the more energetically accessible band states of the thiocyanide, bypassing the barrier between the two band maxima, and then continue into the thiocyanide layer. So on the left, we have a picture that visualizes this better. These are the holes that are then going into this band tail state area, which then very nicely flow into uh, the through the conductor circuits and to the overcome the barrier. And on the right, there is the data of the XPS spectra showing the presence of the tail states. These are again taken from the paper that this presentation is discussing. So finally, of course, we make a PVC PV tandem device with the help of a cuprous oxide copper thiocyanide for the cathode, removing the gold and a perovskite solar cell. And the goal is to to combine the photo voltages to exceed that for splitting water. And device is then tested at an AM 1.5G spectra and at a two electrode configuration. And the performance achieved by the group Pan et al. That made the paper is that they had operating current density of 3.72 milliamp hours per centimeter square, and they had a solar to hydrogen efficiency of 4.55% STH efficiency. So I think the final discussion that this paper brings about is that copper thiocyanide can act as an effective hole selective contact, which can significantly improve the fill factor of these photocathodes by firstly suppressing recombination and giving better performance, and also being more transparent, enabling better performance by being utilized in a tandem cell. Second is that the mechanism or the mechanistic perspective, where you see that there is band tail transport and the discovery of how band tail explain the fact that we are able to overcome the barrier between the valence band maxima and the misalignment of the valence band maxima. And this just highlights the importance of defect states and density of states within the gap to reorganize energy for the reorganization of energy or transport pathways. Then we see that they practically brought about a cell which could bring about 4.55% solar to hydrogen efficiency, and it shows the viability of these type of cells and the possibility for having complex device architectures. This efficiency was among the highest for oxide-based photoelectrodes in unbiased configurations. And then the paper talks about how the limitations of the setup that they have come up with is due to possibly optical losses or catalyst overpotentials or suboptimal voltage matching. And they suggest improvements and future work on better design, like monolithic design, better HER OER catalyst, and tuning band gaps for Fermi complex. So, in conclusion, the paper shows how copper thiocyanide can function as a very effective, transparent whole transport layer for cuprous oxide photocathodes and can improve in extraction of charge and reduce recombination as compared to standard gold contacts. And it gives detailed shows about how detailed electronic characterization reveals band-tail states within the copper thiocyanide band gap, and which can help mediate efficient whole transport from cuprous oxide, overcoming interfacial energy barriers. And then it shows how a PEC-PV tandem device can help unassisted solar water splitting with a 4.55% solar to hydrogen efficiency, and highlighting the potential of interfacial energy with whole transport layers for complex PEC systems. Thank you.